this topic is going to look different for a second, and then we will definitely tie it back into what we learned in section 3.1. So we got to get some new definitions here. And before I start with any of them, I just want to kind of say up front that a lot of the stuff in this chapter, and this section in particular, going into the next few sections actually as well, is that a lot of the ideas are fairly straightforward, but then trying to make them concrete and precise can be difficult, okay? So a lot of the things you can sort of say in layman's terms really easily, but if you want to try and make it precise for a computer, then it takes a significant amount of effort, okay? So here we go. We have to define this first word here, which is a matrix. So a matrix is an array of numbers called entries or elements. So entries or elements in the matrix. Matrices look like this. The size of the matrix is the number of horizontal rows by the number of vertical columns. Okay, so each of these matrices, they often have the brackets or parentheses. I prefer the brackets, but I've seen them with parentheses. It's not terribly wrong. What is the size of each of these? Okay, so this first one has 2 rows and 3 columns. It's a 2 by 3 matrix. B has 3 rows, 1, 2, 3 rows, and 2 columns. It's a 3 by 2 matrix. This one has 1, 2, 3 by 1. This is sometimes called a column vector. Okay, sometimes called a column vector. And this is a 1 row by 3, 1 by 3. This is often called a row vector. So if you sort of feel like this has something to do with vectors and stuff that we did in Calc 3, you are absolutely right. Okay, one more word here. An n by n matrix is called square. So none of these are square here. If you have the same number of rows and columns, something like this, that would be a square matrix, right? Just that thing by itself. Okay, now what are we going to do with these? So suppose that we have a system of m equations and n unknowns. So x1, x2 through xn are the unknowns, and a11, a12, all of the a's are my coefficients, and then the b's are the coefficients on the other side. We're going to define the coefficient matrix, okay, of this system is the matrix of the aij's. Okay, so these are the a11, a12. This is a m by n matrix, as you can see, so it's m by n. And this is going to be called the coefficient matrix, okay? And I have a couple notational points to make here, which is that if you want to build up a matrix out of the entries, then you use this notation here. So A equals Aij. So you just put sort of a variable thing in place with Ij, I being the rows, J being the columns, just kind of building one up out of entries. Then if you'd like to refer back to the entries of a matrix, you put it in parentheses here. So if you put the matrix A in parentheses with an ij, you're referring to the element of A in the ijth spot. Okay, so there we go. Yeah. So just to be clear about what I mean by that, suppose we have this matrix A here, 4, 1, 5, negative 2. What is A, 1, 1? Well, this is the matrix A, and so this thing is the 1, 1 spot. This thing is the 1, 2 spot. This thing is the 2, 1 spot, and this is the 2, 2 spot. Now, one more thing before I move on to this next part, which is our book makes a big deal out of this. It is very typical to use bold letters for matrices. And I certainly did that in a couple things here. I did that down here with B. But it's hard to write that, so I'm going to generally use capital letters for matrices, with the one exception of row vectors and column vectors. We'll kind of deal with that as we go. Try and take it from the context, what kind of thing you're talking about, okay? The next deal is that we can take matrices and we can partition them, okay? And so think about when you're in an office and the little cubicle walls are called partitions. Well, here's a little partition thing right here. And what we're saying here is that I have a matrix A and this other little matrix B, and you squish them together into one bigger matrix, and you've got a little partition thingy in the middle. And the sizes have to be right to make this work, but if it does, then you're allowed to do that. And when we do that, we get another thing for this system above. So here's my system back here, okay, with m equations and n unknowns. We're going to define the augmented matrix. So the augmented matrix is this AB thing where we're essentially taking the coefficient matrix with a little bar, a little partition, and we're putting the B matrix over here. Okay, it's called an augmented matrix, and this is really just a really fancy way of writing a system without any of the variables, okay, or any of the signs. And so this isn't a hard thing, this is an easy thing. So for example, here's a system, 2x plus 7y equals 3 and x minus 3y equals 5. This augmented matrix is just 2, 7, 3, 1, negative 3, 5. Okay? And the whole point of doing this is that back in the previous section, we had these sort of elementary equation operations where we knew the things that we could do to a system to not change its solution. Well, it turns out that all of those things translate over to matrices very well. And so the elementary row operations here, are the exact same things, except instead of calling them equation operations, we're calling them row operations, and it's the exact same three things. So we're going to multiply any single row of A by a non-zero constant, or we can interchange two rows of A, or we can add a constant multiple of one row of A to another. I think I had maybe two of those reversed in the last time we said it. And why do we care about this? Well, here's why we care. A definition is, two matrices are called row equivalent if one can be obtained from the other by a finite sequence of elementary row operations, and if the augmented matrices of two linear systems are row equivalent, then the two systems have the same solution set. That isn't a definition, that is a theorem. My mistake. Okay, so what we're saying is if I do a bunch of row operations on the augmented matrix of this particular system, then I can row reduce it to make it something much prettier, and it's going to be a lot easier to work with than the thing we did in the past. Now, I believe this actually is the same system that I did before, but let's do the row operations on it, and let's just kind of see that it's easier. Okay, so we'll first build the augmented matrix, which is 1, 2, 1, 4. Then 3, 8, 7, 20, and 2, 7, 9, 23. This is a whole lot easier to do when you are just worrying about the things in the spots and not trying to worry about all the variables and stuff, okay? Now, the algorithm for making this look like a much better matrix is to sort of go for this thing first, okay? So that thing is a 1. I'm going to use that now to kill off each of these two things, all right? Now the notation that I'm going to use is I'm going to use negative 3 times row 1 plus row 2. We're going to put that into row 2. So that's the notation that we're going to do. So we're going to multiply a constant multiple of row 1. We're going to add that to row 2. And these are the elementary row operations. Row 1 stays the same, 1, 2, 1, 4, 2, 7, 9, 23. And here we go. So negative 3 times 1 plus 3 is 0. Then negative 3 times 2 is negative 6 plus 8 is 2. Negative 3 times 1 is negative 3 plus 7 is 4. Negative 3 times 4 is negative 12 plus 20 is 8. There we go. Now we'll do negative 2 times row 1 plus row 3. Store that in row 3. Okay, so we're adding it to another row. And by the way, don't do subtraction on these. While you haven't necessarily broken anything, you'll break something that we do later. So remember, add a constant multiple of one row to another and then put it in this spot, okay? And when I do that, what do I get? Am I going to run out of space here? No, I got lots of space. Okay. 1, 2, 1, 4. 0, 2, 4, 8. Okay. And then I'm going to do negative 2 times 1 plus 2 is 0. Negative 2 times 2 is 4. Negative 4 plus 7 is 3. Negative 2 times 1 is negative 2 plus 9 is 7. Negative 2 times 4 is negative 8. Negative 8 plus 23 is 15. Okay. The next, we're going to go after this thing. We're going to make that thing a 1 now. So I'm going to do 1/2 of row 2. Put that in row 2. 1, 2, 1, 4. 0, cut that in half, cut that in half, cut that in half. All right. So I have a 1 here and a 1 here. I'm going to try and kill this thing. So let's go with negative 3 times row 2 plus row 3. Put that in row 3. And I'll go through this algorithm more in detail in a bit, okay? 1, 2, 1, 4, 0, 1, 2, 4. Okay. So let's see. Negative 3 plus 3 is 0. I didn't explain this here. Negative 3 times 0 plus 0 was 0. So if I have this thing as 0 already, it's going to maintain zeros as I go down. Okay. Then I have negative 3 times 2 is negative 6 plus 7 is 1. That's good. And then negative 3 times 4 is negative 12 plus 15 is 3. Okay, now the corresponding system for this is 1x plus 2y plus 1z equals 4, and 1y plus 2z equals 4, and z equals 3. Now at this point you can do back substitution, and if I were a computer person, I probably would do that because that algorithm is going to be faster in terms of computer time. But because I'm a math person, I'm going to keep going a little bit, and I will discuss in more detail later in the section what exactly I'm going for here. But what if I didn't want to back substitute? Could I kill off some of these things using these variables? And the answer is yes. Okay, so here's what I'm going to do next. I'm going to do, and I'm going to keep going down here, negative 2 times row 2 plus row 1. Now that seems like an odd thing to do. Why would I want to go back up? And the answer is this 0 isn't going to affect that 1, right? Negative 2 times 0 is 0, plus 1 is still 1. And so as I sort of work back up, this all stays the same. Right? All that stays the same, and I'm only going to have to change a couple of entries. Okay, so next, I have the negative 2 times row 2. So negative 2 times 1 plus 2 is 0, okay? Then negative 2 times 2 is negative 4. Negative 4 plus 1 is negative 3. And negative 2 times 4 is negative 8 plus 4 is negative 4. All right, so now I sort of have that one cleared out. I'm going to go after these two next. So let's do 3 times row 3 plus row 1. Put that in row 1. Okay, so I'm going to, rows 2 and 3 are going to stay the same here. All right, 0 plus 1 is still 1, 0 plus 0 is still 0. So 3 times 1 is 3, plus negative 3 is 0, so that one's gone. And then I have 3 times 3 is 9, 9 plus negative 4 is positive 5. Okay, so check that one out. That first row says x equals 5. That's really nice. And one more here. Let's go with negative 2 times row 3 plus row 2. Put that in row 2. And I think we're going to end up in a really good spot this time. Okay, so I have 0, 0, 1, 3 1, 0, 0, 5. Okay, and then we'll do the middle one here. 0 plus 0 is 0. 0 plus 1 is 1. Negative 2 plus 2 is 0. Okay, now for the last one here. Negative 2 times 3 is negative 6. Negative 6 plus 4 is negative 2. And this system is x equals 5, y equals negative 2, and z equals 3. So check that out. I've done these row operations until I got to something that is significantly nicer for me to handle. Now, we're going to have in the next couple videos, we're going to have some names for exactly what these things are, and we're going to discuss some computer things to help us do that, okay? So I'll come back and I'll see you then.